So, yeah, as Mark has indicated, we're going to be giving us a variety of talks throughout the workshop that sort of touch on some of the basic points of Tephra work and Tephra chronology. And so what I'll be talking about here, thank you, is really just an overview of Tephra sampling, field, and laboratory observations. There'll be a number of more detailed talks throughout the workshop that will cover various topics that I'll go through in this presentation. Okay, so we'll talk a little bit about what Tephra can tell us. We all have various interests in Tephra. We're not all physical volcanologists. Some goals of Tephra chronology, which I think is sort of the tie that brings us all together. Some characteristics of a Tephra deposit, field observations and sampling, some laboratory observations and analysis, and then at the end, if there's time, sort of just a slide on pulling all of these things together. I'm sort of always ranting about how important it is to use multi-parameter characterization instead of, for example, just one characteristic like geochemical signature. Okay, so what can Tephra tell us? A lot, actually. No matter what our interests are in Tephras, whether we're volcanologists or geochronologists or otherwise, we can get a lot of information out of a Tephra, including the magnitude of the eruption, so things like thickness, distribution, volume, class size, plume height, things like that. Also, the physical character of the parent magma, and maybe this is something that the physical volcanologists are more interested in, but the characteristics from this are very diagnostic. So things like vesicularity, grain morphology, petrography, geochemistry, and also the timing of the eruption, as well as the eruption frequency. Something I'm really interested at the Volcano Observatory is how often do volcanoes erupt, and so I'm using Tephras to do that. Okay, so the big goals of Tephra chronology, and again, I'll point these out because I think this is the term, the word that pulls us all together is the chronology part. This is what we're most interested in. So one of the goals is to uniquely identify Tephra layers or disseminated Tephra layers, okay? And to correlate these regionally, and when possible to determine their numerical ages. So these things together are a huge goal of Tephra chronology, and so in order to be able to do this, we have to first characterize the Tephras. And so detailed sampling, description, characterization, or analyses are really important pieces of information that can link us back to information about the erupting volcano, about the character of that erupting volcano. It can help us with our Tephra stratigraphic correlations, and it also more recently helps us develop and validate dispersion and fallout models, which has become a really big deal in the Tephra world. So, characteristics of a Tephra include both physical and chemical characteristics. In terms of physical characteristics, we think of stratigraphic context, which is really, really important, and I feel like one of the pieces of information that running a Tephra lab I often don't get. I don't often see the metadata associated with where the sample was collected in detail, and then some of the stratigraphic context information. Basic things like deposit color, color of individual components, from juvenile components to lithic components, thickness of the deposit, whether or not you think it's over-thickened or reworked, as the samples that examples that Andre just showed us. Componentry, what's in the Tephra deposit? What are the co-magmatic minerals, both their relative abundance and then just their presence? Also particle size and grain morphology, texture, density, all of these things together help to characterize a Tephra. Some of the chemical characteristics include glass geochemistry, but also co-magmatic mineral chemistry, and sometimes whole rock geochemistry. Yesterday on the outcrop, we were talking about how volcanologists don't often do geochemistry, but I do on all the samples because my job in the field is to work with all of the other disciplines. And so if I'm talking just about Tephras, then I'm talking about glass geochemistry mostly, but none of my other colleagues think in glass geochemistry, they're thinking in whole rock. And so I actually do whole rock on all the Tephras I work on, but it's because I'm working very close to the volcano. So I'll talk a little bit about that. And then age. however we get it, a number of ways. This is probably the most important thing. This is what most people are interested in, is what's the age of this deposit, so that I can know the age of the deposit that I'm interested in, whether it's volcanic or not. So this little box down here is sort of the big rant, that in order to fully characterize or have a robust characterization of a tephra, it's really a multi-parameter approach that begins in the field and goes all the way through laboratory analyses. And it's all of these things together that help to characterize a tephra, not any one individual part. And there's some characteristics that we lean more heavily on, but we really need to focus on the sort of the multi-parameter approach. So in order to talk about these, I thought we would just go through some slides talking about field observations, also talking about some laboratory observations and analyses. But I want to emphasize, and I think we've been talking about this yesterday in the field and even here today, that cross-discipline training is really important. So I encourage all of you, and I see that it's happening a lot, but maybe encourage in the future more groups working together in the field, not just sending each other data or samples, but actually getting into the field, looking at the deposits together so that we can understand and respect how we have collected the samples, and then you have better confidence in doing your analyses. So I think that's a really important thing. And sometimes it's impossible because we're obviously located all around the world, but when possible, I think it's a good idea. So field observations, in terms of stratigraphic context, we're talking about things like, what are your GPS coordinates? Now, sometimes this is difficult if you're trying to find information out of older papers, but in today's world, it's, like I said, just part of the discipline. Keeping track of exactly where your sample site is really important. Providing stratigraphic sections, whether they're schematic sections or photographs that are annotated, always with scales, is very helpful. What's the depositional environment? Did you get this out of a peat core, an ice core? Was it water lane in a marine or lake core deposit, or a subaerial deposit? This also is important in terms of documenting the environment and understanding the depositional environment. So are you near topography? Are you in a flat area? So knowing those things, understanding those things is going to help to better characterize and certainly to better correlate deposits across a region. Other field characteristics include, is the deposit sorted? Most tephra fall deposits are sorted. That can be kind of messed up when you're in very proximal locations, but generally well sorted. What are the bedding characteristics? Fabric, thickness, contacts, physical continuity. These kinds of things, again, there's a lot of information here, and it's, okay, that works. But if we can get into the field with each other and start learning some of these terms, it can be really helpful. For example, working with archaeologists in the field, I benefit from learning how they date samples, because it's very different than how I do it, in the same way that I can be training on some of these terms and we can all start speaking the same language. So here's an example of a field context where we have a lake core. So in proximal settings, it's quite obvious to identify tephras because they're coarse-grained and often thick. So in this particular core, it's pretty easy to pick out the tephras, but there's some subtle difficulties here that you may not recognize a tephra, or you may think that a fine-grained tephra is in fact a distal tephra when it could in fact be from the very near proximal source and a coelutriate kind of a fall. So there's lots of complications there. There's also some complications in a core where you only have a 3-inch or 1-inch or whatever your diameter core is in determining continuity. And so whether or not this deposit is continuous over a whole area is really hard unless you core many places in the lake, and that can be expensive and time consuming, so not often the case. And here's another core that's sort of a nightmare because I don't know what's not tephra. There's just so many different layers in there, and so it's just really having lots of good photographs and I'm thinking about that particular environment and whether or not there's water rushing in through a stream and redepositing material, and there's just a lot to think about in this particular environment. So with lake cores, often if you don't have visible layers, which are easy to pick out, sometimes you can just use clastic texture. If it just feels gritty or clastic in your fingers, that's how we can find them. Often we see layers that are disseminated, then you have to think about, well, what does that mean? Is that reworking off the landscape? Is that multiple eruptions from the same volcano over a short time period? And how do you sample for that? Cryptotephras, do we really just not even see them? I mean, are they just individual shards, or are they just blending in with the host sediment and so you can't see them? Things like magnetic susceptibility, which I have shown here. There's a stratigraphic column, and then the magnetic susceptibility signature off to the right side is a really excellent indicator of volcanic ash in a lake core and in a marine core. We've done some studies where it's 99% of the time high MS equals tephra, even if you can't see it, and so you can hone in on those areas and sample. Some people will use X-ray radiometry, so they're actually X-raying the core to identify tephra, as I'll show a picture of that in a little bit. And then handheld, so I'm still thinking of in the field, a handheld XRF, so you're sort of scanning over the core and looking for clastic material. Is another way to identify tephras that may not otherwise be easy to identify. Here's an example of some marine core. So we're looking in plain view at the surface of I think a 3-inch diameter core, and just showing some of the complexities and things that someone like me who's working in a lab really needs to understand the depositional environment and what you think as the expert who collected this core or this sample. If you have deposits that are irregular or deformed like this, what do we think is happening? Is this a process of pulling the core, or is this something that happened during primary deposition? How do you date things like this? So for example, in this disseminated tephra here again, are we talking about reworking off the landscape, or are we talking about numerous tephras from the same source or nearby sources erupting over time, and how do you sample for that? And certainly, how do you date for that? You're going to get a range of dates instead of a specific date. So keeping track of these kinds of information, I think, are really important so that when we're ultimately correlating things, we've got it all intact. So here's an example of where the host sediment and the tephra are very similar in color, and you may initially not see that. So in this case, it's a peat core, and the sample itself is quite coarse, and so we were able to texturally feel it. But sometimes you really can't tell what's there. Here's just a terrestrial section on a beach cut, just showing the mantling topography, the classic mantling topography of tephras. And obviously, when we're flying by, we wanted to land here because we could see these light colored tephras. So those were the ones that said, yep, this is a good place, there's nice stratigraphy. But if you're in a mafic province and you're flying by, for us, that's kind of how we do work. We may have said, it doesn't look like anything. A lot of our work is kind of recon level that way, and we land where it looks interesting, and sometimes we get lucky. So ice cores. I'm not sure how often you get these really nice layers in the ice core like this. Probably more often that's not the case. Is that true? We'll let Andre talk about that a little bit later. So you either have visible layers in ice cores, and I'm not really sure what a disseminated layer would look like. I guess sort of just a gray area in the core. But using volcanic sulfate aerosols, analysis of this is a good proxy for tephras, and so this is a common usage in ice cores to indicate eruptive activity. Just some more examples, some possible complications. So often you can have color changes throughout a tephra, and that's either telling you that there's multiple emplacement units and you need a subsample. In this case, it looks a little bit mottled, and so I might think this is a little bit reworked, and so how am I going to sample? Oftentimes, color change comes with just differences in grain size or density, and so sometimes, I'll just note this, and then I get into the lab and I can look under the microscope and have a better idea. But noting all of these things in the field is really important. If you don't have it then it's hard to interpret in the lab. Here's a situation where, in a proximal setting, kind of like where we were yesterday looking at these sets that are all related to each other. This is a sequence that if I were 100 kilometers away, I probably wouldn't recognize it. Where the beginning part of the eruption down here is actually a little bit coarser grained, fine, and then we have this dry magmatic eruption, and all of this oxidized looking stuff is actually all lithic material. This is a caldera forming eruption at Akitan volcano, and so we know that this sequence in here represents the collapse of the vent walls and then re-eruption of that, and then this upper part is a fine-grained accretionary lapilli bearing unit that's really fascinating, but at 100 kilometers away, I really have no idea, and I thought it was a good point yesterday that we are focused volcanologists in the near proximal, and so I can interpret this, but in the distal part of the deposit, I may really only see the magmatic component because this is so lithic rich, and I expect those are denser and are going to fall out more quickly. And so just noting these things is really important. I think a lot of people are focused on the Aniakchak tephra, and it's really the one component of the tephra that goes far, far away. But for those of us who are working proximal to the volcano, we see a lot more complexities than people see at distance. And so making note of those, I think, is really, really important, so that when we ask ourselves, does it make sense that this is Aniakchak or some other source, if you're talking to someone who's working near source, you can get those answers, whether it makes more sense or not. So here's just the same deposit, maybe a few kilometers away, and clearly it's really reworked here, and it's really difficult to know what to sample. So things can get pretty messy out there. This is just pointing out, again, the physical continuity across an outcrop, really important to work all over the place. We often get criticism with lake cores, at least. I don't know about marine cores, but it seems to be the same argument that you're just sticking a straw in the mud, and how is that representative of the distribution of that deposit? Well, we have to do both kinds of studies, but preservation in the lakes and marine cores and ice cores is often much better than on the landscape. So, but just pointing out the physical continuity, in this particular slide, you can see things like sample grading, the nice fall fabric, things that some people may not be familiar with if you aren't sitting and looking at tephra deposits all the time. So working with people and really starting to recognize these makes a big difference when you're submitting samples for analysis. I just wanted to point out the significance of thickness and grain size. I mean, I think this is obvious, but I just want to be broad brush here and just make sure people understand that reporting thickness is really important. But if you know something about the depositional environment that tells us it makes sense that something's over-thickened or under-thickened, we need to know that. So if you're just reporting a thickness of 3 centimeters, but you didn't tell us that it's somewhere near a topographic high or on a top of a hill, it's hard to answer the question, does it make sense that this deposit is related to that volcano? And so, I mean, just reporting it is one thing, but saying something about the depositional environment is another. Okay, so I can't get into all the different types of sampling. Obviously, we all have our techniques, and we want to start standardizing some of those. At the end of this workshop on Thursday, we will be having a hands-on. Steve will be leading a hands-on sampling session, and this will be a good opportunity to talk about the specifics. So here I'm just going to be mainly talking about what to sample and how much to sample. I probably get more questions about this than anything else when someone calls and says, I need you to help with this sample, and they want to know how much. Well, it really depends. So in terms of what to sample, really important to sample clean, representative bulk materials. I've had troubles with, or tell us if you didn't do that. I've had troubles with my own colleagues who will handpick pumices out of a deposit, and when I'm trying to ask questions like, does it make sense that this deposit goes with this other deposit when one sampled in bulk and one sampled hand-picked pumices? Well, no, it doesn't make sense. I would say they're not related. There's no matrix to this deposit, and this one's all pumice. When in fact, I just wasn't aware that they were hand-picked pumices. So, I mean, I think this goes for all types of sampling. Did you just take a small sample out of the middle, or did you take a sample out of the entire section? Just be really clear about where you're sampling. This idea of sampling uncontaminated material, well, sometimes we don't know. But down a microscope, we can often tell. So this isn't the biggest problem because you can usually say, okay, under the microscope, nope, that's definitely not volcanic, and so we can just get rid of it. But so there are times that you're going to need to sample the entire sequence because we want the full particle size distribution. And you want to make sure in those situations where the coarser phenocrysts are at the base, you want to make sure to get those instead of avoiding them. I guess what I'm pointing out is it's okay to have a little bit of contamination in your sample just to make sure that you're getting all the bulk materials, because if you need to do crystal separates and you've avoided sampling those crystals because they're at the base and too close to the host sediment, you may miss a really important part of that eruption. And then something I do frequently because I stand up against really thick deposits is I subsample If I suspect compositional zoning, I never have any idea if it's going to be zoned, so I have to figure that out. So I'm definitely a splitter. In this case, it's kind of obvious because of the color change, but even if it was a homogeneous white deposit, I would have sampled it in at least 3 spots, the upper, the middle, and the lower, and then I would test for compositional zoning. As soon as we can say it isn't there, then, okay, the next spots I'll maybe change my sampling technique. But certainly initially, I think it's important to subsample. And then with disseminated deposits, for example, if you think that there are multiple eruptions over a close time period, or you know that from the historical record, it may be worth subsampling. You can always recombine, but you can't resplit. Okay. So I want to talk a little bit about some aids in identifying and characterizing tephra, so some techniques that we might use in the field and in the lab. Also physical tools for identifying and characterizing tephras, and then just some guides, this concept you talked about earlier of fact sheets or guides for being really consistent. Okay, so I don't know how, what tool is used for measuring sulfate in ice cores, so I didn't have any picture to put up here. Maybe Andre can talk about that. But things that you could use in the field are this handheld XRF, I guess not in the field for the X-ray radiometry, but identifying tephras that you may or may not see in the core can be done using X-ray if you have such a tool. And then magnetic susceptibility, we happen to have one in the field here, but it's maybe higher resolution if you do it in the laboratory, and is always an excellent indicator of tephra layers in cores. Things that we might do in the lab is almost always, the first thing I do in the lab is I have to break it apart. I can't see anything if it has fine ash covering everything. And so I do a lot of sonication, physical agitation, sometimes acid washes if you think your sample is really altered. But rarely do I need to do that with young tephras, but certainly we're talking about all ages of tephras. In an ice core or very, very tiny samples from lake cores or marine cores, you may need to, if you don't even know something's there, you may have to, melt this material out, filter it, and use a centrifuge to concentrate it. This is pretty typical practice for tiny samples. And then what I do with almost all of my samples is wet sieving. It's the only way that I can physically see anything, and so the result of that is just these 3 grain sizes here. This being the sort of the most useful in terms of looking at things under the microscope, because it's both big enough and it sort of represents 1 grain size that doesn't bobble around on the slide when you put a cover slip on there. But yeah, this is sometimes my first opportunity to really even see anything. I have to clean off all the fine ash. Other tools, just a basic binocular microscope. So I think sometimes, depending on your discipline, you might think, oh, I'm just going to leave that to the physical volcanologists or people who are, like looking down microscopes or know something about it. But in fact, you can learn a lot from just a basic binocscope in terms of identifying tephras. Again, probably the second most question I have is this even a tephra? And I think most people can figure that out pretty quickly just using a binocular scope. I think using a hand lens is pretty common, but honestly, I'm not even very good at that. So I just clean things up and look under the binoc scope. And then, of course, using a petrographic microscope is much more detailed, and you can identify, crystals and certainly beautiful images of glass shards and crystals that are coated in glass, which is also an indication of a primary deposit. And then if you're fancy schmancy, you can use an SEM, or if you just have very small number of shards, that's a nice way of immediately indicating whether or not you've got a tephra. Oops. Some other methods in the lab for characterizing a tephra might include density separation, so where you're trying to isolate the glass away from the crystals, just really for improving your probe analysis experience. I'm lazy, so I don't do it very often. If I have a sample that there's plenty of glass or that's easy to identify, in other words, it's vesicular glass, then I will skip this step entirely and mount up bulk materials and then just know that I'm going to hit some crystals and get rid of them later. Some people are less lazy, like in Andre's lab, where they sometimes will isolate 99 or 100% splits. But the reason for that is because they're using the glass splits, the pure glass splits, to do other analyses that are bulk analyses like ICP. But if you're just doing electron microprobe analysis, it's not totally necessary always to do this step. It takes some time and you have to deal with some nasty chemicals. Magnetic mineral separation using a Franz. If you want to isolate your oxides and do oxide analyses, which is becoming quite common and very useful in characterizing tephras, using a Franz might be a useful tool if you have one. And then also just particle size analysis, whether you do that on your own or send that to a lab. So some geochemical tools might include the electron microprobe or the use of an ICP or laser ablation ICP-MS. And then I just threw in a picture of what a probe mount looks like. And I throw in these little things that I know most people know it, but I also know there's a variety of people in here that maybe have never seen a probe mount before. So that's basically what it looks like. That's a carbon-coated mount. Okay, so getting back to this concept of guides, I feel like as a government employee, part of my job at the USGS is to do things using standard techniques through time. The lab's going to be there long past me, and we need things to be comparable. And so everything I do in the lab is guided by some sort of guide like this. So I put up this as an example of terminology. And I will argue that this is a problem, even in the most disciplined people, because my own colleagues will use sedimentological terms over volcanological terms, and it just makes communication really hard. Field notes become complicated, and so just agreeing on some terms and making it clear what they are seems simple, but everyone has to agree. We still have personalities to deal with. Color. This is an obvious one, using a Munsell color chart. Everyone's aware of these. This is really, really helpful. I can't tell you how many students I've worked with who, I mean, boy, Zev and I, we can never agree on colors. So this is a really helpful tool. As well as the guides that I received from Andre's lab that Elmira put together years and years ago. I use this religiously because it's the only way that I can be consistent about my descriptions. Otherwise, sitting there and trying to train students becomes sort of a nightmare. Other things in the lab, macroscopic observations. So I try to do these in order. First the big things, and then I look at the small things. And so things like componentry. I have the advantage of coarse material, which everyone doesn't. So you may not be able to do this on fine-grained sediments, certainly not with your eyeballs. So how many different components in there? How many different juvenile components are in there? I usually don't do componentry with lithics, but sometimes that's important, especially if they're really unique. So this is not just for coarse material. We can also use a binocular microscope and see that there are clearly two different kinds of pumice in this deposit, or maybe a scoria and a pumice. And so this is, I think, a situation with the Aniakchak tephra where everyone's characterizing the light color pumice, but there's actually a dark component in there that sort of gets erased. And it's important because it's part of that eruption. Just noting the color of the components here. So now we're out of the field and we're not just noting the color of the deposit, but we're noting the individual colors, both of the altered surfaces, or if they're altered, and the interior fresh surfaces. So both of those is really important. If there's any degree of alteration, this is just any possible characteristic I can find, I'm noting in a database. What is the particle size of the sample, as well as sometimes density. I don't always do that, although I really should. Microscopic observations using both a petrographic microscope and a scanning electron microscope. So what are the shards of the shard morphology look like using those guides? What color is the glass? What else here? Just basically, yeah, I guess color, glass, shard morphology, abundance of minerals, presence of minerals, comagmatic minerals, and then any alteration that you see. I mean, this is an important step because then you know whether or not you can even analyze it geochemically. And then just the same thing using an SEM. If you have the advantage of that, it's probably not the most important thing to have an SEM. It's just convenient. And in terms of geochemical characterization, I know that there'll be other discussions about different techniques, and Andre brought up INAA. I'm sort of just listing the main tools that people are focused on today. And I wanted just to point out for some people that may or may not be aware that the first step in geochemically characterizing something is the major and minor oxides using an electron microprobe. And there's all sorts of controversy about that not being good enough, and it's often not distinct enough to distinguish tephras over over large regions. But we still have to do it. It's kind of our baseline. And so in Alaska, I'll talk about this when I talk about our database in Alaska. We are dealing with huge volumes of tephras. We're trying to get out to source volcanoes and understand eruption frequency and do basic characterization. So we have not taken the step towards more detailed trace element analyses, which we're certain are needed, but it's just a matter of time. And people actually to get these things done. So there's always this initial need to do the basic major and minors, because these other methods are just getting you the trace elements, and you still have to have the initial characterization using probe on glass and or crystals. Iron titanium oxides often. So yeah, I just put up here the difference between some of these methods. This is becoming quite popular, and others will be talking about this in detail over the course of the workshop, and those will be exciting talks. But grain discrete analyses are probably the most important type of analyses we can do. I didn't put on ion probe here, honestly, because I can't even think of affording it. So, but people who have we even have a tool, but I can't afford to use it. So that should go on here as well. Okay, and then finally, age determination. So there's a number of ways that we can do this, and there are a number of people out here today that will be talking about different techniques. But there's both direct dating using things like glass fission tracks, and that's typically on older tephras. Well, not typically, but is on older tephras. Dating of comagmatic minerals using a number of different methods, and we've got some great talks coming up. But most often we're using indirect techniques. Quite often in the Holocene we're using radiocarbon material of paleosols or buried soils beneath tephra layers. And we saw a really nice example of an old one yesterday. Correlating, probably also number one, is correlating a tephra of known age. This is most often what people are interested in when they ask you where the sample came from. They want to know if you've collected the same sample and have it characterized well enough to match to yours, and it has an age associated with it. Age modeling has become a big deal, and it's pretty amazing because, for example, in a marine or a lake core, you can date things down to every millimeter. So every millimeter of sediment, you can say, has an associated age based on modeling, and calibration curves of a radiocarbon curve. And then magnetostratigraphy for older deposits as well. And then I'll put up one more slide. Yeah. So I just wanted to focus again on this concept of multi-parameter characterization. So not just using any one of these things, but keeping in mind all of these things together. And the person that's in the field is absolutely as important as the person in the laboratory, and working together is really important. So I tend to create these tables, these correlation tables, where I'm not confident in a correlation until I've lined up a whole number of physical and chemical and age information, and I can be confident in that correlation. And so just wanted to give an example of what that looks like. That's it.